Hello. This will be a demonstration of proposition 14 from book 10 of Euclid's Elements, which says that if four straight lines be proportional, then if the square on the first exceeds the square on the second by a square on a straight line commensurable with the first, then the square on the third will likewise exceed the square on the fourth by a square on a straight line commensurable with the third. But if the square on the first exceeds the square on the second by a straight line on a square incommensurable with the first, then the square on the third will exceed the square on the fourth by a square on the straight line incommensurable with the third. So we'll have four straight lines, A, B, C, and D. They will be proportional. So A is to B just as C is to D. Like that. Then we'll also have two other straight lines, E and F, set out such that A squared is greater than B squared by the square on E, and C squared is greater than D squared by the square on F. So let's set out those lines. And F will go right about that long. Okay. Then either A will be commensurable with E or A will be incommensurable with E. And what we want to show is that likewise, if A is commensurable with E, then C will be commensurable with F. But if A is incommensurable with E, then C will also be incommensurable with F. Now, because A is to B just as C is to D, we were given that, we can also say that the similar rectilineal figures erected on those proportional straight lines are also proportional. That's what proposition 622 tells us. So, because A is to B just as C is to D, then we can also say that the squares on these lines are also proportional. So that A squared is to B squared just as C squared is to D squared. Now, A squared is equal to B squared plus E squared. That's just another way to describe what we were given. We were given that A squared is greater than B squared by E squared. Another way to say that, then, is that A squared is equal to B squared plus E squared. And likewise, we were also given that C squared is equal to D squared plus F squared. Again, that's just rephrasing what we were given. If C squared is greater than D squared by F squared, then that's the same as saying C squared is equal to D squared plus F squared. So then we're going to substitute those sums of squares for A squared and C squared, so that we can say B squared is to E squared. B squared plus E squared has 2B squared, the same ratio which D squared plus F squared has to D squared, which then also means separando, if we take the consequence from the antecedents and compare those to the consequence, then we know from proposition 517 that E squared is to B squared just as F squared is to D squared. So you notice we're just taking away from the sum of B squared plus E squared, we're taking B squared from that. And likewise, we're taking from D squared plus F squared, we're taking D squared away from that, so that we can say, again, according to proposition 517, that E squared is to B squared just as F squared is to D squared. From which also follows that the straight lines on these proportional squares, those straight lines are also proportional. Proposition 622 also tells us that. So that because E squared is to B squared just as F squared is to D squared, we can also say that E is to B just as F is to D. But we were also given that A is to B just as C is to D. So now what we have is the setup for an X-equality move. We have that A squared is to B squared just as C squared is to D squared. And in step 2, we found that A is to B just as C is to D. And we found in step 2 that E is to B just as F is to D. We can also invert that proportion according to the porism of proposition 5.7, so that not only is E to B just as F to D, but that's the same as saying B is to E just as D is to F. So we have that A is to B just as C is to D, and that B is to E just as D is to F. So we can cross those middle terms, b and d, to say x-equality, according to proposition 522, that a is to e just as c is to f. And that's perfect, because we know from proposition 1011 that if four magnitudes are proportional, as we have a being to e just as c is to f, then if the first is commensurable with the second, the third will likewise be commensurable with the fourth, but if incommensurable, then incommensurable also. So that because a is to e just as c is to f, we've just shown that, then if a is commensurable with e, c will also be commensurable with f, but if a is incommensurable with e, then c will also be incommensurable with f. Again, that's according to proposition 1011. And that is what we set out to prove. We set out to prove that given the setup of four proportional straight lines and the squares on the antecedents exceeding the squares on the consequence by certain other squares on certain other straight lines, then if a is commensurable with e, then c is commensurable with f. But if a is incommensurable with e, c is incommensurable with f. And having just shown that in step 3, we're therefore done with the proposition. Therefore, etc. Q, E, D. That one, I'm sorry, that was a little bit rambly. That's my fault. I apologize for that. If any of that wasn't clear, again, the comment box is always open, so feel free to ask any questions about this proposition if you have them. Now, there is one thing that remains sort of lingering, and that is, you may be wondering, how exactly we obtain the straight lines E and F. How we get straight lines such that the squares on them are equal to the difference of two other squares. And according to that curiosity, Euclid has kindly supplied a lemma before this proposition that tells us exactly how to do that. So having finished the proposition proper, I'm going to cut the video here and move on to demonstrating that lemma. So now let's demonstrate that lemma of proposition 1014, which tells us, given two unequal straight lines, to find a straight line such that the square on it is equal to the difference or the sum of the squares on the two given straight lines. You'll remember the impetus for this lemma was the existence of the lines E and F from proposition 1014 proper. It was kind of a wonder how you might obtain those lines. And so that's what this lemma supplies. At least that's what the first part of it supplies. The second part supplies an additional construction that gives you a straight line whose square is equal to the sum of two given squares as opposed to the difference of two given squares. So, as the proposition says, we're given two unequal straight lines, A, B, and C. And our task is to find a straight line whose square is equal to the difference of a squared and c squared, and another straight line whose square is equal to the sum of a squared and c squared. So we've got to find one line such that the square on it is equal to ab squared minus c squared, and we've got to find another line whose square is equal to ab squared plus c squared. We'll begin with finding the difference of two squares, since that's why this lemma exists in the first place. We'll begin by constructing a semicircle on the line AB. We can do this if we bisect AB, and then from that midpoint, taking that midpoint as the center of a circle, taking that midpoint as the center of a circle and taking half of AB as the radius, we're going to describe that semicircle according to postulate 3. Next, we're going to fit a straight line AD into this semicircle, which is equal to C. And we know how to do this according to proposition 4.1. And finally, let's join the line DB. Now, because the angle ADB is a right angle, we know it's a right angle because it's an angle in a semicircle. And proposition 331 tells us that the angle in a semicircle is always a right angle. So ADB, that angle is a right angle. And being a right angle, it then follows that the triangle ADB is a right triangle, which then means, according to proposition 147, that the square on the line AB is equal to the sum of the squares on AD and DB. So that, because AD squared is equal to C squared, because remember, AD is equal to C, so their squares are also going to be equal. We can substitute that in and say that AB squared is equal to C squared plus DB squared. So then rearrange things according to common notion 3. We're going to subtract C squared from both sides so that we can say DB squared is equal to AB squared minus C squared. So now we found a line, DB, whose square is equal to the difference of the squares on the two given straight lines, AB and C. That's the first half of our lemma done. Now the second half of our lemma, we'll want to find another straight line whose square is equal to the sum of AB squared and C squared. So we'll begin doing that by erecting from the point B on the line AB, a line BE, which is equal to C. And then we're going to join the line AE. Now also, because the angle ABE, that's a right angle just by virtue of how it was constructed. BE was constructed perpendicular to AB at B, so ABE is a right angle, which then means that the triangle ABE, that's a right angle triangle. So again, according to proposition 147, we can say that AB squared plus BE squared is equal to EA squared. But again, remember, BE was made equal to C, so BE squared is also equal to C squared, so we can just substitute that in and say that EA squared is equal to AB squared plus C squared. So we have found another straight line as EA, whose square is equal to the sum of the squares on the given straight lines AB and C. And that is what we set out to do in this lemma. We have found two straight lines, DB and AE, which are equal to the difference of the squares on AB and C, and equal to the sum of the squares on AB and C, respectively. DB was found equal to AB squared minus C squared, and AE was found such that its square is equal to AB squared plus C squared. And that being what we wanted to find in this lemma, we're done with the lemma QEF. A couple things I want to say about this one. First is that this is the first lemma I'll have demonstrated. Lemmas become not infrequent, starting with book 10 onwards. How I've chosen to add the lemma to the proposition is I've appended it to the end of the video. So first is that, do you like that? The order of the book is the lemma precedes the proposition in this case. In other cases, the lemma will come after the proposition in which it's used. So if it's, I think my plan will be to put lemmas after the propositions, just so the proposition can be front and center, and I won't confuse people by starting off with a lemma when they thought it was going to be a proposition. The second thing I want to say is not asking for advice, but a challenge I want to issue to you. I say that you can do this sort of construction. You can find the line DB, whose square is equal to the difference of two given squares. You can find that line without using book 3. You'll notice the crux of the construction of DB was based on the fact that the angle ADB is a right angle. And we can say that it's a right angle because of proposition 331, because the angle in a semicircle is always right. But I say to you that you can accomplish the construction of DB in a more difficult way using only propositions from the first 2 books. This was something that I had found about a year or so ago, and I enjoyed finding it quite a lot. It was just a very fun challenge. So that's a challenge you would like to take up, please do. It's really fun. Proofwriting in general is very formative, especially, and it's very helpful for studying the elements. That's all I've got to say about this lemma, which means that's all I've got to say about this proposition. So I'll end the video here and move on to proposition 1015.